Can y'all hear me? Wait, so can everyone actually hear me? Is this actually broadcasting? All right. That was quite the production. So I currently have this set up with my iPad doing the video and sound. I have my Windows PC in my room actually running the stream, and then my Ubuntu computer with the screen next to it. So that's fun, getting Apple, Ubuntu, and Windows to work together. Alright, so here. Hopefully you've had time to look at your warm-up. So if you haven't started that now, kind of look at your warm-up and work on that. I'll solve it in just a second. A few things to kind of think about. They have put out a little bit of information. I know the most recent word is possibly 3 weeks out. I know the CDC has said something up to 8 weeks off. So I have no idea what's going to happen with all of this. I just figure let's just keep going because it's probably not going to be very normal for a little while. So I guess just tell me where you're at. Did anyone have a chance to did anyone have a chance to do the warm-up yet, or are y'all still looking at that? Why are you not showing? Alright, I don't know why my video is not showing up on my computer. Yeah, I'll give people a second to actually show up over here. What are you confused about? you got a really big answer. All right, so there, I think I finally have a setup that works for me. All right, so let's just go through and try to do this. So is equilibrium vertically different from horizontally? The equilibrium will still be the same. So when we're talking about the speed of the block at the spring equilibrium position, what do we mean by the spring equilibrium position? Everyone doesn't have to answer all at once. I think there's a pretty big delay here for me. Maybe that's what's going on. So let's just do this. So the speed of the block at the spring equilibrium position, so the spring equilibrium position is when our displacement from equilibrium is 0 meters from the equilibrium position, obviously. So we're trying to find the speed of the block when the spring reaches equilibrium. So we're probably going to be using conservation of energy, so total mechanical energy before equals total mechanical energy after, assuming that we have no force of friction. If we have no force of friction, then the work done by friction is 0. All right, so conservation of energy as the spring launches upwards. So total mechanical energy, so we have spring potential energy, we have gravitational potential energy, we have kinetic energy, spring potential energy final plus gravitational potential energy final plus kinetic energy final. So when we're talking about at spring equilibrium, so we start with this thing being compressed downward. So we do start with spring potential energy. We can choose whether or not to start with gravitational potential energy. I'm just going to call the lowest point 0 and make this a little bit easier. And then it's pushed down and released. So because it's released, it's not moving initially. So when we're talking about this, A is talking about when we're at spring equilibrium position. So when we're at the spring equilibrium position, that means we don't have any spring potential energy. But because we called our initial height 0, that means we will have a final height, and we will be moving for our final position. All right, so I have 1/2 spring constant times that distance from equilibrium squared, all equal to mass times acceleration due to gravity times final height, plus 1/2 mass times the final speed squared. All right, so we don't really have anything we can cancel out from all of these. We could do something like multiply everything by 2 to get spring constant times that distance from equilibrium squared is equal to 2 mass times acceleration due to gravity times final height plus 1/2 mass times final speed squared. All right, so we're trying to find that final speed. We know the spring constant k is given. We push this thing down a distance d, so spring constant times distance d squared is all equal to 2. The block has a mass m. We're on Earth. We end up at a final height of d. We launch up a distance d from whenever we launched, plus 1/2 mass m times that final speed squared. All right, so we can go through, we can subtract this term over. So spring constant times distance we're compressed squared minus 2 mass times acceleration due to gravity times the distance we compress this thing is all equal to, and why did I leave a 1/2 there? That should just be mass times final speed squared. And then I can divide mass and take a square root. So spring constant times distance squared divided by mass minus divide out mass, so 2 times acceleration due to gravity times that distance d is final speed squared. So our final speed is going to be the square root of this whole term. Spring constant times distance squared divided by mass minus 2 times acceleration due to gravity times distance. That's where you're talking about getting a big answer, then that was going to be it. So the spring equilibrium position actually won't be the maximum velocity. The highest speed is going to be the next one when the system is in equilibrium, where we go from initially the spring is accelerating upwards when it's launched by the spring, but once we go through that equilibrium position, there's going to be more force down on the block, and so the block is going to start slowing down. Yeah, so that's the spring equilibrium. It's when the spring is not extended or contracted at all. That's a good way of putting it. All right, so B, we want to try to find the speed of the block when the system is in equilibrium. So when the system is in equilibrium, that means our net force is 0. So our net force is 0 newtons when we are at equilibrium. All right, so our net force is 0 newtons at equilibrium. So that means we're going to be trying to balance our forces here. So I know my spring force holding up is going to be balanced by the weight of the block down. So spring force is that spring constant times the distance from equilibrium. Actually displacement, but we're really caring about magnitudes here, is all equal to mass times acceleration due to gravity. So the thing we really need is how far this is from equilibrium, right? That's what we're using in our equations here. I need the distance from equilibrium is the important part to solve from this. So the distance from equilibrium is going to be mass times acceleration due to gravity divided by the spring constant. And you may be a second late. I did erase that 1/2. Yeah, I caught that. So you are correct. It's just mass times final speed squared. All right. So we have how far we are from the equilibrium position. So again, just like before, we can use our conservation of energy. So spring potential energy initial plus gravitational potential energy initial plus kinetic energy initial equals spring potential energy final plus gravitational potential energy final plus kinetic energy final. All right, so we'll use our same initial values as we did up here. So I'm going to call my spring potential energy 0 to begin with. Not 0, not spring potential energy. We're going to call our gravitational potential energy 0 to begin with, because we're going to say this is a 0 meter height. We're released from rest. Now, when we get to the block equilibrium position, the spring is still going to be compressed, so I still have that. My gravitational potential energy won't be zero because I've launched a certain height from where I started, and we're going to be moving, so I do have a final kinetic energy. So this is a little bit messier. So my initial spring potential energy, just like before, 1/2 spring constant times, I'm pushed down a distance d squared, all equal to my final spring potential energy, 1/2. Why do you always want to use kinematics? Kinematics is unnecessary. 1/2 spring constant times the distance we're at now is going to be a little bit of a mess because we started out, actually no, we can just use this. What am I saying? Yeah, so mass times acceleration due to gravity divided by spring constant all squared, plus gravitational potential energy is mass times acceleration due to gravity. Our final position, this is our final displacement from equilibrium, but this isn't our final height, right? So we have this thing launches up a distance d from when it's fully compressed to the spring equilibrium position. We end up at a position of mg divided by spring constant from equilibrium, which means this height is going to be the difference in these two values. D minus mass times acceleration due to gravity divided by spring constant. So yeah, that's a little bit messier than I think I intended to make this, but we'll just go with it. Distance minus mass times acceleration due to gravity divided by spring constant, all plus 1/2 mass times that final speed squared. All right, not a lot we can do to make this really nice looking. Let's do the same thing where we multiplied through by 2. Spring constant times distance squared is all equal to spring constant times mass squared acceleration due to gravity squared divided by spring constant squared, plus mass times acceleration due to gravity times d minus mass times acceleration due to gravity times mass times acceleration due to gravity divided by spring constant, plus 1/2, not 1/2, multiplying everything by 2. I missed my 2's here also. It is Monday after the break. Minus 2mg multiplies by 2, mass times final speed squared. We can simplify a few things down here. Spring constant times distance squared is all equal to spring constant divided by spring constant squared. So I have spring constant times mass squared acceleration due to gravity squared, plus 2 mass times acceleration due to gravity times distance. What am I doing? This should be divided by spring constant. Spring constant squared, so I have mass squared times acceleration due to gravity squared divided by spring constant, plus 2 mass times acceleration due to gravity times distance the spring is compressed, minus 2 mass times acceleration due to gravity, mass squared, acceleration due to gravity squared, divided by a spring constant, plus mass times final speed squared. All right, so I can do 1 m squared g squared over k minus 2 m squared g squared over k. So that would be minus m squared g squared divided by a spring constant, plus mass times final speed squared is all equal to our spring constant times distance squared. And we're just kind of stuck with a few things here. Let's just spring constant times distance squared plus mass squared acceleration due to gravity squared divided by spring constant minus 2 mass times acceleration due to gravity times distance, mass times final speed squared. So I end up with spring constant times distance squared divided by mass plus mass times acceleration due to gravity squared divided by spring constant minus 2 acceleration due to gravity times distance is all equal to final speed squared. So my final speed is the square root of all of that. Spring constant times distance squared divided by mass plus mass times acceleration due to gravity squared divided by spring constant minus 2 times acceleration due to gravity times distance. I think that's right. If someone sees a mistake in there, tell me. Again, it is the Monday right after a break. Also, I could probably write a little bit bigger. Can you actually see that on your screen well? So on a horizontal spring, we normally don't deal with gravitational potential energy if it just slides across the surface because its height is not changing. I could say it has a gravitational potential energy on a horizontal spring. It would just be the same initial and same final, and so the math would just subtract out. Yeah, I could factor a few things. I have more important things I'd like to talk about today. All right, so C is a little bit more straightforward than B was. We're going to try to find the maximum height that this thing goes to. So C, I'm going to be a little bit lazy here. I'm just going to say at the very, very beginning, all I have is spring potential energy. And then when I reach my maximum height, all I have is gravitational potential energy. So all of my spring potential energy I started out with turned into gravitational potential energy when I reach my highest height. I go up, reach my highest height, stop before going down. The spring isn't stretched or compressed, and the speed is 0. All right, so 1/2 spring constant times that distance squared is all equal to mass times acceleration due to gravity times final height. And this is really straightforward. All I have to do is divide over mass and acceleration due to gravity. So my final height is going to be spring constant times the distance the spring is compressed from equilibrium squared divided by 2 divided by mass divided by acceleration due to gravity. Out of the types of things that I would expect you to really see on the AP test, this not so much, although I would expect you to be able to know how to use conservation of energy. This is honestly the difficulty of math I expect you to really see on the AP test. All right, then D wants us to find the new maximum height if the spring were compressed twice as much. So we could do this a few ways. Let's just go through and do the math again. So we still have the same thing where spring potential energy turns into gravitational potential energy. So 1/2 spring constant, but I compress this thing twice as far. mgh final. So 2 squared is 4. So I have 4 times 1/2 spring constant times distance squared, which means I have to end up going mass times acceleration of gravity times 4 times as high. So we go 4 times as high. But just a pretty simple, straightforward thing saying distance is squared, height isn't. So when I plug in a 2, 2 squared is 4. So I end up with 4 times as much energy. Height isn't squared, square rooted or anything, so I have to go 4 times as high. So I'll give you a minute for my video to catch up. It seems like the video is about 10 or 15 seconds delayed on my end. Any questions on the warm up or any questions on what's happening? So it really ends up just being times final height here. But I see I have 4 times as much energy. I know mass isn't changing. I know acceleration due to gravity isn't changing. So if I have 4 times as much initial spring potential energy, that means I end up with 4 times as much gravitational potential energy. Because mass and acceleration due to gravity are constant, the only place I could put that 4 is right here. So my final height has to go up times 4. Here's my face reveal. I got a haircut. Happy. Okay, so that's a very good question on the AP. I didn't know about the graphing questions. I haven't actually tried them. Um, if it does involve actually posting an image and you can't do that, then I will try not to assign those. Um, we'll see. I just assigned those to kind of see how everything would go and if you would be able to do that. So I'll assess that kind of later. Just try to do it if you can. If it turns into a problem, just write that in the answer that you couldn't figure out how to actually make a picture, and then I won't grade that one. uh, yeah, when I get 1,000 Patreon supporters, then you'll have my face in the corner. I'll give you a tour of my house. All right, so don't do that. All right, so now I'm going to work through some of the questions on the AP Classroom. There's a few I would like to do, if this would actually pull up. I'm just kidding, I do not have a Patreon. Alright, so right now you should be going to the College Board website. I'm going to try to work through a few of the ones on this College Board website. So the AP Classroom. Where is my cat? So right now, go to the College Board website and try working on those. I have a few select ones I'm going to go to. I think the first one I'm going to do is probably just right here. Probably just the first one that's listed, number 1 on your assignment. All right, so I think this one is going to be question 1 on your page. Let's see. Hopefully you can read this well. I kind of disassembled a monitor partially in order to run it through my laptop. So the screen might not look the best, but you can at least read it. 19 questions, a lot are multiple choice. We'll go through, I'm just going to see how it kind of goes, and I'll reevaluate. All right, so looking at question 1, so we have a pendulum consisting of a sphere suspended from a light string. So again, light string, pretty much no mass. I don't know if it shuffles the questions for you. Okay, question 2 then. So this is question 2. All right, so again, so light string means pretty much massless string. Small angle with respect to the vertical. So again, that small angle is meaning it's simple harmonic motion. So it's not simple anymore if we pull the angle more than 10 degrees. So small angles means simple harmonic motion. Our equations work. The sphere is replaced with a new sphere the same size but greater density and is set into oscillation with the same angle. How did period, maximum kinetic energy, and maximum acceleration of the new pendulum compare to those of the original? All right, so we changed the mass, but what does mass actually change? Why are you dark now? Oh, you're not far enough. All right, so we changed the density, and I think I just said that. We changed the density, which is obviously going to change the mass. Density is mass divided by volume. So they said the... Where are you? The density... Yeah, same size but greater density. So density goes up, but same size, so volume is unchanged. That means our mass has to increase. All right, so we're talking about a pendulum here. So a pendulum, if you remember, you have your formula charts. The period for the pendulum is 2 pi square root of length of the string divided by acceleration due to gravity of whatever planet or object we're on. So mass changed, but that does not affect my period equation, so I expect the period of the pendulum to be constant. Alright, so I could do that. I can look at my maximum kinetic energy. So when I release this, I start with potential energy. So spring potential energy is turning into kinetic energy. Not spring, gravitational potential energy is turning into kinetic energy. So mass times acceleration due to gravity times initial height is 1/2 mass times final speed squared. Now we see mass goes up. But whenever we do this, what are we trying to see? Oh, kinetic energy. So I'm just going to leave this as final. There we go. So I have more potential energy. That means my final kinetic energy is going to be higher. So that maximum kinetic energy is going to be bigger. So then we just have acceleration to look like. So that means we're probably using net force equals mass times acceleration. So when we're pulled back to a certain angle, we have the pendulum here, like this. I'm going to have some tension force holding this up that is less than the weight of this. All right, so this is going to swing down this way, which means just like a ramp, I'm going to want to split everything up parallel to the motion or perpendicular to the motion. Tension is already perpendicular to the motion. Gravity isn't. So I'm going to need to split up gravity into a part of gravity this way and a part of gravity that way. So let's draw my triangle a lot bigger. So I know my angle theta from the vertical. I'm trying to split up. So yeah, mass would have canceled out here, but it's trying to see what happens to our final kinetic energy. So we're not trying to find the final speed, but the final kinetic energy. So we're not going to end up canceling out the mass. All right, so we have this force of gravity down. Let's draw that nice and long. This line and this line are both down, so these have the same internal angle right here, force of gravity right here. I'm trying to get the amount of force of gravity going this way and the amount of force of gravity going this way. These are going to be at right angles to each other. So this side right here is my adjacent side. So this side is my opposite side. Adjacent is cosine, opposite over hypotenuse. Adjacent over hypotenuse, what am I saying? Opposite is going to be sine, which is opposite over hypotenuse. So adjacent is going to be dealing with cosine, so FG cosine theta. This is going to be dealing with sine, FG sine theta. All right, so when I look at this, I have a tension this way, which is going to perfectly balance out with these two forces when we're stopped. I need to put this in the picture. So when we're stopped, these two forces are perfectly balanced out because, again, at the highest point, we know our speed is 0 meters per second. Because we have 0 meters per second speed, I know my centripetal acceleration, speed squared over radius, is 0 meters per second squared, which means my centripetal force is 0 newtons. So because of this, these two forces have to cancel out. So my tension cancels out with the weight times cosine of the angle, which means the only thing I have left over is weight times sine of the angle is my net force. So net force equals mass times acceleration. Net force is weight times sine of the angle is mass times acceleration. Mass times acceleration of gravity times sine of the angle equals mass times acceleration. Mass divides out. So our acceleration does not depend on mass, so acceleration is constant. Now, we could have gotten that result a lot faster by just realizing gravity is what's pulling this down. Whenever I have gravity pulling two different masses, it's going to pull them equally. It's March 23rd a B-Day. So it doesn't sound like we're going to be back next week either. The CDC is saying pretty much shut down everything for 8 weeks. I don't know what our school is going to do, but they make it sound like possibly 3 weeks or more. So I'm just kind of going by whatever day is most convenient to me. So I was just planning on doing AP today and dual credit MST tomorrow and alternate something like that. But yeah, everything is going to be pretty much shut down for a while. Like every single school field trip has been canceled through April 30th. It's just one of those things. Whenever I kind of saw all sports were canceled for a month, that's when I realized we're not coming back very soon. Obviously, keep track of what the school district actually says, but yeah, summer break. They haven't said anything about summer break being cut off. I kind of think because, as they said, teachers, this was a teacher work day. So we're working, so I don't think they're going to extend everything because that would mess up contract situations. So I think they're going to try to do some sort of online teaching for a while. I haven't seen anything official about that, but that's probably what we're going to move towards for a little bit. And I haven't heard anything about moving back the AP tests other than College Board saying that they're thinking about changing things. But yeah. Alright, so yeah, what answer choice is that? So it is, which one? Period is the same, kinetic energy is larger, and maximum acceleration. So the answer is D. My channel sponsor is Physics. Physics, the thing you want to be doing on a Monday morning and now afternoon because my stream didn't work. All right. I mean, yeah, I'm assuming for a lot of the on-level classes, they're just going to have some sort of online type thing that we do. But I don't know. We're supposed to have meetings about it online tomorrow, so we'll see. Alright, so the next one I want to do, where did I put my paper? Put it right there. I want to do the very next one, number 4. So kinetic energy. The parts of D, what? Oh, okay. Yeah, so the first question, kinetic energy, because we're not looking for final speed. If I was looking for final speed, I would say mass times acceleration due to gravity times initial height equals 1/2 mass times final speed squared. So when I look at this, I would say, okay, mass divides out, so they have the same final speed, right? So same final speed. But because kinetic energy is 1/2 mass times speed squared, if they have the same speed, then the object with more mass will have more kinetic energy. So it should be acceleration is the same. We'll see the period is the same, but we're going to see a larger final kinetic energy, whichever answer that corresponds to for you. Yeah, a lot of people are working from home. My wife actually teaches a college class, and there's a good chance the students are just never coming back for the semester. Why are you not moving? What games? You can watch me play some really old school RPGs. You want to watch me play some RPGs from the 80s and early 90s? So I'm working through problems on the AP website. Mr. Lambert would have to put those up for you though. So when I go through them, the question will be right here, and you can work through that, but you won't be able to answer it on the actual website. This is really not going to let me scroll. Alright, so this one, I think it should be number 4 for you. Wait, maybe, yeah, I think it should be number 4 for you. Could be wrong. But yeah, pendulum has a length L, bob of mass M. Which of the following is true about linear momentum of the bob as it swings from its highest to lowest points? Alright, number 3. Yeah, I don't have a real nice, easy way of looking at this. They don't let me actually preview the assignment. So number 3. Alright, so what's happening to momentum as the pendulum moves? So whenever we kind of break this down, let's just kind of look at, we know momentum is mass times velocity. Momentum, mass times velocity. So the mass isn't changing. But what's happening to our speed? $50 subspecial. It would have to get past my other YouTube channel. I had a channel that got up to 700 subscribers before YouTube deleted it. So then I'll do a special. Alright, so mass is constant, but our speed is changing. Alright, so as which of the following is true linear momentum as it swings from its highest to lowest point, so the speed goes up, so that means momentum goes up. So momentum increases. Is the momentum staying in the same direction or changing directions though? Um, YouTube didn't like my bot, my automations. It's a little similar to if you look at my actual image for my channel. It's actually encoded for something if you can figure out what that means. That's kind of along the lines of what my channel was encrypted messages. All right, so here we have a momentum this direction. Then we get to the bottom, our momentum is going to be in this direction, everything not to scale. So yeah, the momentum is changing. So we see momentum goes up and changes. So momentum should increase and change, which for me increases in magnitude, changes the direction. So for me, it's B. I don't know what it is for you. Yeah, if you decode it. It's not the hardest thing to decode. Why don't you let me scroll on here? Let me scroll. Whatever. Okay, not going back to the, let me scroll again. What else I want to do? I think I said 5. What is taking you so long? So the assignment is due tomorrow night by 11:45 is when I put it. I'll kind of reevaluate. We'll see how that goes. Oh man, this computer is slow. All right, so what number is this for you? Apparently it's question number 0 for me. However that works. I think it should be 4 for you. All right, so number 4, a simple pendulum and mass hanging on a spring both have a period of 1 second when set into a small oscillatory motion on Earth. They are taken to planet X, which has the same diameter as Earth, but twice the mass. Which of the following statements is true about the periods of the two objects on planet X when compared to their orbits, their periods on Earth? Give you a second to think about that. sine 4? Sine 4 degrees or 4 radians? Gonna have to be a little bit more specific there. All right, so we're put on planet X, same diameter, but twice the mass. So what are we changing? All right, so force of gravity, gravitational constant, times mass of the object, mass of the planet, divided by radius squared. So g is a constant. I didn't change the mass of the object. I didn't change the radius, how far we are from the center of the planet, but the mass of the planet did increase. So yeah, so if I have a bigger force of gravity, so acceleration will change. So my force of gravity will change, my acceleration will change. Are we going to be accelerating faster or slower? Like a higher rate of acceleration or a lower rate of acceleration? So we see our acceleration went up. So is it going to take more or less time, do you think, to complete a cycle if you have a larger acceleration? Well, we see a bigger acceleration, so I'm going to expect the time to go down. And one way of kind of thinking of this is if you put a mass on a spring and there is a larger acceleration due to gravity, it is going to stretch the spring out more. As the spring stretches out more, there's going to be a larger force, and it's going to balance around a different equilibrium around a larger force. So because we have bigger forces, this is going to move the thing faster, which means it's going to take less time, which means the period of the pendulum is shorter. That of the mass on the spring is the same. So yeah, so the acceleration due to gravity goes up, so period on the pendulum, 2 pi square root of length divided by acceleration due to gravity. We see acceleration due to gravity goes up, period of the pendulum goes down. But we have our spring equation, 2 pi square root of mass divided by spring constant. Didn't change the mass, didn't change the spring constant, didn't change 2 or pi. So the period of the pendulum will go down, period of the spring goes up. No, there is no 2020 rule. You're just not allowed to use the restroom ever until quarantine is over. Otherwise, everyone everywhere will have the COVID-19. All right, I think number 4 was relatively straightforward. Let's see if this will actually let me scroll now. And it is not. And my computer sucks. I'm pretty sure I am nowhere near getting monetized. I mean, you could look backwards in time, but yeah, we end up having shorter period for the pendulum, but equal period for the spring. What next? Then I was wanting to do 7, 9, and 13. So those are the other ones I want to do. Then I think I'm going to be done for today. Which one is 7? All right, so yeah, so this one well, it's number 7 for me. I think it's number 6 for you, maybe. Yeah. Whichever one this is for you. The answer for 4, I don't know what the exact letter is for you, but the period of the pendulum goes down, but the spring has a constant value. All right, number 6 then. All right, so a simple pendulum consists of a bob of mass 0.085 kilograms attached to a string of length 1.5 meters. The pendulum is raised to a point Q, which is 0.08 meters above its lowest position, and released so that it oscillates with a small amplitude theta between the points P and Q as shown. So P right here, Q right here, lowest point in the motion right here. All right, so this one, does it let you actually draw these on yours, or does it expect you to actually download the image and edit it somehow? Because I was not sure about this. Yeah, just use ASCII symbols to draw a free body diagram. Yeah, you could probably manage to do something like that. I don't know how you would get the vertical answer. So if it asks you to solve something, try to show your work as much as possible. It doesn't have to be perfect formatting. You can use like the caret key, you can use the times key. Just try to write the answer as best as you can. But yeah, I guess if it's a thing that has anything that you have to write out, you could take a picture of it and put it into Google Classroom. So that's one thing you can do. If it's a thing that expects you to draw, you can draw it out on a piece of paper, take a picture of that, and upload it into Google Classroom for today, the 3/16, whatever I called the announcement for today, and then just mark it as complete, and I can look at it from there. That would be something you could do if it's an actual picture. Alright, so let's do this. Free body diagram showing and labeling the forces acting on the bob in each of the situations described. So A wants a free body diagram when we're at point P. So at point P, we want a free body diagram. So I have gravity pulling down, and I have a small amount of tension holding up. Right, so point P is right here, tension pulls up and right. So I have a small amount of tension because the tension isn't holding up the entire weight. Some of the weight is going into moving down, while only part of the weight is going into stopping this mass from moving. And then two, what is when it's at the lowest point of its motion. So at the lowest point of its motion. So again, here we're going down, but we need to start going up. So we're going down and we need to start going up, which means I have to have a bigger force up caused by my tension than my force of gravity in order to turn this thing. To make it stop going down and start going up, I need a bigger upward force. All right, so if you can't draw that on there, or if you can't come up with some sort of ASCII text way of drawing it, you can just write it on a piece of paper and turn it in through Google Classroom through today's assignment. I don't know how you write on it. You can try using different ASCII symbols like I showed in the chat right there. You could use this. You have a vertical symbol that you can use for upward arrows. So if you are really creative, you could come up with something using arrows, but otherwise just solve it and post the answer on Google Classroom. So on the College Board website, they actually have the forces being the same, but that is incorrect. I don't know if they just weren't grading based on that. But I need a bigger upward tension. There has to be a bigger upward tension to go from going down to up. I need a bigger force up that's going to stop my downward motion and start upward motion. So because it's not moving directly sideways. So yeah, the force of the tension is the force that moves the mass up. All right. So then B wants us to calculate the speed of the bob at the lowest position. So this is pretty straightforward. I think this question came from an AP test before Physics 1 when there was actually a lot more math. I'm going to be a little bit lazy here and just say we start with gravitational potential energy and that all turns into kinetic energy. So mass times acceleration of gravity times initial height. 1/2 mass times final speed squared. Now this one I can divide out mass because I'm trying to find final speed. I can multiply over 2 acceleration of gravity times initial height equals final speed squared. Or final speed is going to be the square root of 2 times 9.8 meters per second squared times the initial height is at 0.08 meters. And I do not have a calculator over here. But yeah, it should be like 1.25 meters per second. Yeah, 1.252. So the final speed is 1.25 meters per second. All right. So C wants us to get the tension of the string when the bob is passing through the lowest position, which this is the weird one to me because you're not going to let me actually see this. They actually drew the tension equal to the weight here, and then in the very next part, well, part C, they pretty much showed that no, the tension is not equal to the weight. So yeah, I don't know what they were going at there, but they are definitely incorrect. But they may not have just graded based on that. They may have just been happy to get the forces somewhat correct in the correct direction. All right, so calculate the tension when we're at our lowest position. So we could do this a few ways. It looks like they're trying to get us to solve it using our final speed because we do know our centripetal force is going to be our net turning force, so that's going to be our tension minus the weight. So our tension is going to be centripetal force plus the weight. Which makes sense. The tension has to hold up the weight of the swinging mass and turn it. So we're going to have a bigger tension than our weight. So we have our centripetal force is mass times speed squared over radius plus mass times acceleration due to gravity equals our tension. What is the mass of this thing? I literally just used it, didn't I? 0.085 kilograms. We cannot just use weight is equal to tension because these are not equal. So our yeah, so the tension doesn't equal the weight. So 0.085 kilograms times we're moving at a speed of 1.25 meters per second all squared divided by the string length is 1.5 meters. All right, plus 0.085 kilograms times 9.8 meters per second squared. Yeah, my stand is pretty just rigged together. I really didn't imagine it was going to get this messy, and then YouTube not allowing me to stream from a mobile device until I have 1,000 subscribers was the most obnoxious part. Where is this question? All right, so when you do the math, it comes out to 0.92 newtons. Somewhere around there. And then D, describe one modification that could be used to double the period of oscillation. So D, the period, why did I write an equal? Period of the pendulum is 2 pi times the square root of length divided by acceleration due to gravity. 9 point something. You're using 0.085, not 0.85. Yeah, it's 0.92. They got 0.93 because they use G as 10. Yeah, you can all go get free lunch and breakfast. They don't care how you get there. I don't know when the lunch times are. You should look on the Garland ISD website, though. I know they don't care if you get there by car, walking, bike. If you go there, you'll get food. All right, so yeah, back to this question. We want to double the period. So I could do 4 times the length because 2 pi square root of 4L divided by G. When I take the square root, wow, that is a horrible looking for. When I take the square root of the 4, I end up with 2 times 2 pi square root of L over G. That's one way we could do this. What else could we do? So we could obviously just change what pi equals to, right? So change the value of pi. Or we could just go to a planet with 1/4 the acceleration due to gravity. Would also work. But I'm pretty sure they were looking for 4 times the length. Questions on this one? Just change pi. Pi is exactly 3. Alright, then I want to do, what was this number on mine? That's number 7 on mine. Then I want to do 2 after this, so I'm assuming it's going to be number 8 on yours. Don't die, computer. And my laptop is trying to crash. Come on. Gonna work now. Oh, come on. No, no, no. And you locked me out. Nope. Don't need you. Yeah, sorry, give me a second. My computer's finally responding again. There we go. I have my comments back. Let's go here, sign in. All right, finally. I don't know. Flexible testing options are, they'll come up with something when they come up with something. Honestly, right now, if you see anyone saying anything about plans for the future, it can almost be ignored. Um, yeah, pretty much everything about every plan we have, if you actually read what they say, it's always depending on how everything pans out. So pretty much nothing is, we're definitively coming back this day, or this will officially be back this day. Pretty much everything has been really open-ended about when things will be back. All right, so what number is this for y'all? Number 8? I think this is number 8. All right, number 8. So this is one we haven't looked at a whole lot, dealing with a graph like this. Again, one, when you have a graph, you can draw this one out on a piece of paper, take a picture, and put it in the Google Classroom, and then I can look at it from there. Google Classroom code, you should be in there, are you not? It's where you turned in everything. You were able to turn in the other things unless you somehow got dropped. Oh no, never mind. You're not in my class. That's what it is. Classroom code. All right, so let's just look at this one. A student hangs a 0.125 kilogram object on a spring, sets it into oscillation, and obtains the data for the position and velocity of the object as a function of time shown in the graphs below. All right, so we have a position versus time graph. We have a velocity versus time graph. And so we're trying to sketch potential energy of the the spring Earth system as a function of time, and explicitly label intersects, asymptotes, maxima and minimum with numerical values as appropriate. All right, so we're trying to graph our potential energy. Now, hangs on a spring, oscillates. It doesn't say what type of potential energy of the object Earth system as a function of time. Yeah. Why are you in my way? Spring Earth system. All right, so we can look at this. We have our position versus time graph here. We can kind of decide a few things. So first of all, what type of potential energy are we talking about? If we're looking at the object spring system as a function of time. No, object spring Earth system. All right, so we do have spring potential energy, but what else do we have? We also have gravitational potential energy. So my total potential energy, because we're looking at the spring mass Earth system, my total potential energy is going to be my spring potential energy plus my my gravitational potential energy. Now, what's being turned into these? What type of energy do we have that's being converted into these? Don't think anyone said this yet. But we have kinetic energy that's being converted into these, right? So we have, there we go. Yeah, we have kinetic energy that's being turned into each of these two types of energy. So when I'm looking at my graph, so we're going to try to set this up. First of all, we can kind of put our zeros where we want, especially with our gravitational potential energy. We can choose where our zero height is. But we're looking at our, not position, our velocity right here. So velocity should help me get my kinetic energy. So at 0 seconds, the kinetic energy is 0 speed. So I have 0 joules of kinetic energy. Then I can look at 0.5 seconds, not 0.5, 0.25 seconds. 0.25 seconds, we have, what is this, kinetic energy, 0.125 kilograms, so 1/2 times 0.125 kilograms times the speed at this point. It kind of looks like it's about 1.5. I know it's not perfect. I assume they're trying to get us to think it's somewhere around there. You might say 1.6. Let me see what they're actually going for, what they actually use as the number. Yeah, they did use 1.6. It kind of makes sense. It goes up slightly past the top here, so a little bit above 1.5, so right around 1.6 meters per second squared. Which is right around 1.6 joules. Yeah, DC MSD live stream is going to be Tuesday, Thursday, starting at around 10:30, and then I'm planning on tomorrow around 1 trying to do a tutorial for AP students, and then I'll alternate which day the tutorial is for. I have to see, there's scheduled meetings tomorrow, so I'll kind of see when the meeting times are, and then I can coordinate after that. All right, so kinetic energy, and then we go back to at 0.5 seconds. We're back to not having any speed there, so we're back to 0 joules of kinetic energy. 0.75 seconds. We're also going about negative 1.6, so we're the same speed as we are here, which means I'm going to have the same kinetic energy there. 1.6 joules, and then 1 second, we'll repeat to 0 joules. And we're going to see this pattern is going to just repeat itself continuously. You're getting 0.16. Did I do something wrong? Oh, yeah, it is 0.16. I just wrote it wrong. 0.16. All right, so I have 0.16 joules. So these are the values I'm looking with. So kinetic energy goes from 0 joules to 0.16 joules to 0 joules to 0.16 joules to 0 joules. Now, we know our total mechanical energy is constant, right? As long as there's no friction, we have a constant total mechanical energy, which means if I have 0 joules of kinetic energy and I'm going to have 0.16 joules of kinetic energy, it means my potential energy here is 0.16 joules, which means my potential energy here is 0 joules. Then I lose all my kinetic energy. It's all gone back to potential energy. Then all of that energy went to kinetic energy, so I have no potential energy, and then it's just oscillating back and forth like this. All right, so just kind of a simple sketch because this is going to be a repeating graph. So we go down to 0, mark our points up here. So we'll just say this is 0.16 joules. We have our spring potential energy in joules. We have our time in seconds. Significant moments in time for at least one cycle are going to be this. So I have 0 seconds, then we're counting by 0.25s. 0.5, 0.75, 1. All right, so I start off with no kinetic energy, so all of my energy is in spring potential energy. And then by 0.25 seconds, I have no spring potential energy. Then 0.5 seconds, I have all spring potential energy again. And then 0.75, no spring potential energy. And then 1, all spring potential energy. Now, I see my velocity oscillating as a sine wave, which means we're probably going to see something similar here. So it's going to oscillate like a wave, like this. Yeah, sorry it's taking a little bit longer. You don't necessarily have to watch everything out of all of these. I'm just trying to go through as many as I can. I only have one more I'd really like to go through. I'm trying not to take too much of your time away. I do want y'all to actually unwind a little bit and relax and sleep. All right, so B wants us to sketch the acceleration of the object as a function of time, explicitly label any intercepts asymptotes, maxima, or minima with numerical values as appropriate. All right, so sleep's that thing that I get more of when we're on a break than when I'm working than when I'm on a break. All right, so acceleration. So the easier thing about acceleration is to really look at our force, right? Remember, acceleration is going to be a little bit easier looking at net force equals mass times acceleration. So yeah, I kind of disagree slightly with whatever. So net force is going to be mass times acceleration. So our net force, it's going to be dealing with our spring force and our gravitational potential energy. But whenever we look at this, we can kind of say whenever I hang a mass on a spring, even though the spring is stretched, I can kind of say this is my new equilibrium position. So we can kind of look at this and kind of just pretend force of gravity hasn't pulled my spring down here, and this is my spring equilibrium, and we're just looking at the force of gravity going back and forth. So we can kind of just assume this is only my spring force is causing the mass times acceleration. Mathematically, it ends up working out. I don't want to get too much into that. But yeah, we're just kind of putting our equilibrium position here, and we're going to say there's no forces acting on this other than the spring force. The only point of the gravitational force is changing our equilibrium position. So when we get this, we're trying to get acceleration. So spring constant times displacement from equilibrium divided by mass equals acceleration. So we're going to want to get our acceleration at different positions. Or at different times, I mean. So at 0 seconds, the acceleration is our spring constant, which did they actually tell us? Of time. Oh yeah, we actually have to solve for the spring constant. All right, so spring constant. So I know period of the spring is going to be 2 pi square root of mass over spring constant. I mean, I'm also looking at the answer key they have provided. So I'm making sure I don't do anything horribly stupid. But yeah, divide 2 pi over. So period divided by 2 pi is all equal to the square root. Mass divided by spring constant. Then I can square everything. So I have period squared divided by 4 pi squared is all equal to mass divided by spring constant. I'm just going to flip both sides here, so I have 4 pi squared divided by period squared equals spring constant divided by mass. Then I'll multiply mass over to the other side. So I get 4 pi squared times mass divided by period squared equals spring constant. Now, 4 pi, those are constants. 4 pi squared mass. So we're kind of looking at the force of gravity as just a thing that's moving our equilibrium position. Mathematically, whenever we work this out, we can assume there's no spring force. We can just look at no gravitational force. We can just look at the spring force moving this up and down. mathematically, we can kind of just look at the force of gravity as offsetting the position a little bit, and then once we balance those two forces out as equal and opposite, we just don't care about them anymore. So one thing I can do is if I just call this my equilibrium position, I can cheat a little bit and just call this my spring equilibrium position. So this is, I'm pretending this is where my spring is in equilibrium. And so I'm letting, when I do this, I'm letting my spring force and my force of gravity, these two parts, I'm letting these cancel out. But after this, sometimes my spring force is going to be small, sometimes my spring force is big. And so sometimes it cancels out all of my force of gravity, sometimes it doesn't, and it just ends up working out, just letting these two cancel out, and then the difference in the two is what I'm going to be calling my spring force. And then all of my distances will be from this new equilibrium. I don't know how to prove that directly off the top of my head. 4 pi squared, 0.125 kilogram object, divided by period squared. Now, how can we get the period? So period is the time to complete one cycle. So say from right here to right here is 1 period. Or I could go from crest to crest. Here to here would be 1 period. Or I could go the middle here to the middle here, here, here. But we see from here to here, it takes 1 second to repeat the entire motion. So we should get a spring constant of, I got 4.93 newtons per meter. They got 5, they used G as 10. Alright, so now that I know my spring constant, now I can finally go back up here and deal with my accelerations at different times. So at 0 seconds, my acceleration is going to be spring constant times displacement from equilibrium divided by mass. So my spring constant is that 4.93 times, I'll get back to that in a second, divided by our mass. I already forgot what mass I wrote, 0.125 kilograms. Now, the thing we're going to have to look here is how far we are from this equilibrium position in the middle. So when we look at this on here, we're right here. So our equilibrium position is going to be somewhere, we go up to 1, we go down to 0.5. So my equilibrium position right here is going to be at 0.75 meters. Is that meters? Yeah, that is in meters. All right, so 0.75 meters. So when I look here I'm at the very bottom, I'm at about 0.5 meters. So my distance from equilibrium is going to be about 0.25 meters below equilibrium, right? And I don't think you can even see that. So we're about 0.25 meters below equilibrium. should get about 9.86 meters per second squared. And so when the spring is stretched down from equilibrium, so right here we're below equilibrium, we're at 0.5, our equilibrium is at 0.75, so we're below equilibrium. That means the spring is trying to pull us back up to equilibrium, right? So the spring is trying to pull us back up to equilibrium. All right, so back up to equilibrium, so our acceleration is going to be up. Then I can look at 0.25 seconds. At 0.25 seconds, we're right here, so 0.25 seconds. We're at 0.75 meters, so we're at equilibrium, right? So we're at the equilibrium position, therefore our acceleration is going to be 0. Yeah, your acceleration is actually pretty much g for this one. It ends up undoing the math. So then I get to 0.5 seconds. Now I am back to being, now I'm above equilibrium for the first time. Sorry, not back to being above. So now I'm above equilibrium, so my acceleration is going to be that spring constant, 4.93 times, we're 0.25 meters above equilibrium. We're at a position of 1 meter up, and our equilibrium was at 0.75. So we're 0.25 meters above the equilibrium position. 0.125. So our acceleration will be the same as here, 9.86 meters per second squared. But now we're above equilibrium, so we're accelerating downward. There we go. All right, so we can kind of put this all together. It's going to repeat itself. So, and then at 0.75 seconds, we're going to see again acceleration is 0 meters per second squared at equilibrium. Then at 1 second, we're going to see the motion repeat itself, where we're back to 9.86 meters per second squared up. So I didn't account for the weight in the net force because what I was kind of assuming, I was assuming that this pulls down with the weight and the spring force pulls up. So whatever weight I put on here, in a sense, the spring force is canceling out a part of the spring force is canceling out the weight. So instead of looking at weight, one way of looking at this is seeing where the mass settles and just call that my equilibrium position. So once I call that my equilibrium position, that equilibrium position is due to my weight. So putting my equilibrium position where the mass settles is in effect already accounting for our weight. Mathematically it works. I don't have a proof directly off the top of my head that would do that, but we're not ignoring gravity, if that's what you're concerned about. We're not pretending that the weight is not here. We're just already accounting for the weight. The weight moved my equilibrium position, and then from that moved equilibrium position, I don't need to look at weight anymore. You can Google this, look this up. It's a thing you can do. I'm sure somewhere someone proved it. I can try to find a proof for it, but I just don't immediately know how to prove it off the top of my head without spending a while trying to do it. All right, so let's kind of put this all together. So we have our acceleration, meters per second squared, versus time in seconds. 0.25, 0.5, 0.751. Positive 9.86, negative 9.86. So we start off at 0 seconds. So at 0 seconds, we start off with a large positive acceleration, an upward acceleration. Then at 0.25 seconds, we're at our equilibrium position, so our acceleration is 0. And then we end up going down below to negative 9.86, back to 0, back to 1. Again, we're going to see a sine wave type thing. And pretty much any time you see a pendulum or a spring and you're graphing it, it's going to be some form of a sine wave shifted somehow. All right, C and D, I'm not going to do the whole thing about this, but yeah, they're talking about next the student. Yeah, you can get acceleration from the derivative of your velocity graph, and so yeah, you're going to see you go from a positive sine wave to a positive cosine wave. Next, the student is given a rubber band and is asked to determine whether the relationship between the restoring force exerted by the rubber band and the amount it is stretched is the same as that of an ideal spring. So starting off, we assume an ideal spring, so we assume spring force is going to be spring constant times displacement from equilibrium. So we assume some sort of relationship like this where our spring force and our distance from equilibrium, we expect a linear equation, right? So we expect as distance goes up, spring force goes up linearly, not square to square rooted. And again, my slope is going to be my spring constant here because y equals mx. All right, so we're trying to see pretty much determine whether the relationship is the same for an ideal spring. They're pretty much saying, does this follow Hooke's law? Where an ideal spring, we have a constant spring constant, so I have a constant slope between these two things. So, first thing we should probably think of is, because we're looking at the spring constant, I'm trying to see if it's an ideal spring, it has a constant spring constant. Let's kind of think of what spring constant is. Spring constant is in newtons per meter, or our spring force divided by the displacement from equilibrium. So we're trying to figure out something that we could use in order to determine these two values. So I need to measure force and distance. All right, so we can measure our distance from equilibrium with a meter stick. Now, there's a few ways of getting my spring force here. I'm going to say let's get our spring force with a spring scale. With a spring scale. All right, so why does that look so terrible? All right, so we used spring scales early in the year when we were trying to find spring constant. They're the ones that you pull, kind of like the things that you weigh vegetables at a grocery store. You put it in and then the scale moves. So we could get the distance this thing is stretched with using a meter stick, spring force with a spring scale, and then we're going to need to do a lot of different measurements. So find the delta x and spring force at 10 positions with a distance interval of 5 centimeters or something. So just something like that, where you're just going to say something about measure how far the object is from equilibrium using a meter stick, measure the spring force with a spring scale force gauge. And then once we do that, you can just say find the position, how far we are from equilibrium with a meter stick, find the spring force using the spring scale at 10 different positions, and 5 centimeter intervals. Just something like that should be fine. Collect all necessary data. That's enough to gather the data. Equipment, that's good. And then you can always throw in multiple trials just to be safe. And then D, how should the student analyze the data to determine whether the relationship between the restoring force exerted by the rubber band and the amount of the stretch is the same as an ideal spring? What evidence from the analysis would be used to make the determination? Again, I'm probably just going to go back to my graph here. So because, and anytime you already talk about something and then you need it the next, let's just rewrite it here or reference based on the graph I drew on the previous part. But if you already wrote it somewhere, it's going to be nice to just redraw it. So spring force equals spring constant times distance from equilibrium. So I expect this y equals m delta x. I expect a constant, spring constant. So when I graph this, I would graph spring force versus my displacement from equilibrium. And then we'll see if linear, therefore the spring constant is constant. And if not linear, therefore the spring constant is not constant. So that's one way of looking at it. That's not the only way. You could also put it in a table and see if the values are changing by a constant rate. But something like that. And give any questions if you want. I'm only going to do one more, number 12. The spring constant cannot be constant. A place that you see this would be pretty much any spring. If you stretch it a little bit, you'll see it follows Hooke's law pretty well. But when you start stretching it really, really far, like when the spring itself starts to break, you're going to see the spring force is no longer constant. Or if the spring compresses too much, you'll see the spring force isn't constant. So the spring constant isn't constant. But yeah, so the spring constant does not have to be constant. And in every real world spring, if you stretch it enough, you're going to see the spring constant not be constant. But for small regions, pretty much all springs are going to follow that spring constant value pretty well for a little bit. All right. No other questions on that one? It seems mostly okay. Again, just the biggest thing, make sure you always talk about what you're going to measure with what. You really can just use simple sentences like this. I'm going to measure displacement from equilibrium with a meter stick. I'm going to measure spring force with a spring scale. Find displacement and spring force at 10 different positions with a distance interval of 5 centimeters. That's most of the points. When it says write a paragraph, that really is paragraph. I just wouldn't abbreviate delta x. I would say displacement from equilibrium. But other than that, yeah, it's pretty straightforward like that. So let's look at the last one I want to look at is, I think, number 12 for you. Yeah, number 12. That's a good one because it's showing something that we haven't talked about yet. All right, so we're on question number 0 again somehow. I don't think we're going to do an online AP test. That's just not a thing that would happen. It seems like if everything goes where they do have 8 weeks off, then we would be back in time just for the AP test. It might be shorter than that. If anything, I would anticipate possibly doing AP tests later in the year. But yeah, we just have no idea. College Board hasn't put out any official information yet. So is this one number 12? Yeah, we'll just stream the AP test and I'll work through it as you go through it. All right. So number 12, an object moves up and down the y-axis with an acceleration given as a function of time t by the expression a, which is your position we're at now, is equal to the amplitude of the wave times sine of the angular frequency times time. A and omega are constants. What is the period for the motion? So this sets up a new equation that we have here. Where are we? Yeah, so that's our new equation right here. So this is talking about a sine or a cosine wave. So what position are we at? So my position, how far I am above or below the x-axis, is going to be the amplitude of the wave times cosine times 2 pi times frequency times period. So we're going to be using this equation. We could be given the equation in this form. Here we're trying to find angular frequency. So they give us that equation. So we know our equation is amplitude of the wave times sine of the angular frequency times time. So we want to find the period of this equation. So angular frequency from our formula chart, let's see how they actually have it written. I forget this. Oh yeah, they don't have it written like that. They have period is equal to 2 pi divided by angular frequency is 1 over frequency, which is pretty convenient because omega written right here, I can just put it into this equation here. So my period is just going to be 2 pi divided by angular frequency. So for me, that's D, but I do not know what that is for you. All right, so those were the only ones I had planned to go through today. The rest, try to finish for homework. I'll kind of assess how it went. You can tell me how it goes tomorrow. Tentatively, I am planning on doing some sort of tutorial session tomorrow at 1. I'll reevaluate tomorrow based on when meetings happen. I'll post an announcement at some point when I figure out what time each meeting is actually going to happen. Are there any last minute questions about the assignment or kind of just what's going to be happening in general for class or assignments, things like that? Quick question, explain Hooke's law. Hooke's law is just our spring force equals spring constant times displacement from equilibrium. This is Hooke's law. So everything follows Hooke's law. This equation is always valid. The only question when they ask, does it follow Hooke's law, they're really saying, is our spring constant constant? That's the question they're really asking. So anytime they say, does this expression follow Hooke's law, they're saying, does this have a constant spring force? Just because our equation, a lot of times, y is our spring force, our slope is spring constant, and delta x, our distance from equilibrium, is our x value. So, yeah. What is going to be happening? So, there's a few things. I'm still waiting for word from the district. I personally kind of think this is going to last longer than the numbers they put out. It sounds like we're supposed to be ready to do this for a few weeks at minimum. I'm probably just going to put in some curves for the things that are already done if I figure out it's going to take a really long time because like we're shut out of campus too. So if I'm just going to be stuck here, I'm probably just going to put in curved grades for everything so that everyone doesn't have to worry about continuing to have a 30 while we're out. So I'll kind of evaluate that and put the grades in. Things coming up immediately. Today, do your warm-up, take a picture of it, post it in Google Classroom. As long as you did it and go through and get the correct answer I showed, you'll get a 100 for that. The homework that I posted on AP Classroom, try to do that. If it's something you have to draw on, then you can draw it on a piece of paper, take a picture of it, and post it under the link for today's class, the 316 class, whatever. So you'll write that and post it there, and I can grade that from there. I plan on giving assignments each day. Kind of give me an idea next class, was this too much, too little? Because I don't want to overwhelm you. Yeah, those are things coming up. Probably tomorrow I'll announce when I'll have some sort of tutorial session where you can sign in to ask questions. Hopefully I log in a little bit faster next time that I figured out what I need to do. And yeah, and then Wednesday we'll have another class here, and that one I'll try to be on time. But any other questions? Derive that A sign. I mean, it would just be plus or minus 2 pi. Can we see my cat? Where did my cat go? This is my cat. He always gets really sniffly when the weather changes. Yeah, actually, I don't have a dog. We got a cat because we thought it would be less needy. That didn't work out. I don't want to show you my gaming setup because my room is an absolute mess. So well, yeah, I think that's it. But other than that, if you still have questions, post them on Google Classroom. You can post the questions under the section. Yeah, don't be streaming and driving. But yeah, if you have any questions, just post them on Google Classroom under today's thing. And again, I'll keep you updated on any changes. So if that's it, everyone have a good one.